although those corners portfolio approach or the two fund separation idea is very interesting and very cute, but there is some problem there. There's some limitation of using this model. What are they? The first one is that this approach is very sensitive to the change of input. Now, what does that mean here? Now, let's go back to the original approach of using the estimated parameter. Like here, we have to estimate the expected return and the standard deviation and the correlation for those individual asset class. So any type of the estimation error in turns these are the input parameters and the result will be completely different. So the model to get this corner portfolio like we have here for those allocation about what is percentage weight to get optimum portfolio to meet our target at 8% are quite sensitive to those standard deviation correlation or the return estimation, right? Then any type of the error there will cause the huge difference in terms of the allocation result. Second problem is that again, this model is still a one period model. Okay, so it's a one period. That means that we assume that all the distribution over time is constant. It doesn't change. But in fact, the distribution parameter it change over time. It caused by the market condition or the what we call the economic parameter change. So it is a static approach. Ignore the dynamic nature of the input parameter. Therefore, our result can be used in the very stable period time. So if we facing the very dynamic period time or there's some dramatic change in the market condition, the model may not be accurate. To resolve this problem, we usually use this called the resample or resampling approach to define the efficient frontier based on resampling process. In this resampling process, we use this called the Monte Carlo simulation. Monte Carlo simulation meaning that using a given parameter of, for example, you have the target mean and the standard deviation, and assuming that you have a normal distribution, then you're able to use the normal distribution, that formulation, by putting the parameter there and then simulate the hypothetical sample result. Okay, so those is a randomization, random sample generated from the distribution, and we call the Monte Carlo simulation. Again, we're still using the historical mean and variance, and we use that parameter to generate random sample for say 10,000 times. Then we use that to calculate each sample we calculate allocation weight. Then we repeating the same process for 10,000 times. We get the average weight, right? Average portfolio weight. Therefore, you will have efficient frontier. Okay, like here we got the portfolio 1, 2, 3, 4, 5, 6, 7, and instead of using the one parameter of mean and standard deviation, we look at the average mean and standard deviation to get the average outcome of the efficient frontier. Therefore, this frontier is much more stable than just using one estimate from the sample to put in there. So it's just like a repeating sample for 1,000 times to get a stable efficient frontier. Of course, even though this way can resolve the problem of instability of efficient frontier or optimization allocation, but again, it's still lack of a theoretical basis, and it's purely a numerical approach, and then also is based on historical return data. So this still some drawback. So just remember when we actually when you see what's the potential problem of corner approach or the two-phase separation approach in terms of mean variance efficient frontier, understand the limitation, and usually we ask the question how do you overcome this problem. The simulation is one possible way to do that. Now, certainly to resolve the instability problem of efficient frontier using the historical parameter estimation, there's another model try to solve this problem. Not a numerical model, it's a theory model. It's called the Black-Litterman model. The Black-Litterman model is a very famous model. We're use it for the optimum weight for the optimal portfolio to determine optimal weight. The idea is different from the corners portfolio. The idea is more like using instead of using the historical estimation from historical data for each individual asset class, and here is based on the market condition first. So it's assuming that we have a global market which is is on equilibrium. So it's using the equilibrium asset value implied by the existing market price of the global asset classes. Now, if you look at the global asset classes as a whole over a period of time, it tend to be very stable. We're assuming that the market is efficient. Suppose market is efficient, then the price information from the global market asset class. All right, we talk about asset classes, not the asset itself. Asset classes is like average of that, so it's like a big portfolio. That big portfolio price, we can assume they are the equilibrium price. So Black and Littleman say, well, that's using that and backward, right? Backward to find the asset class optimization. So it's more like a so-called reverse optimization. So next time when people ask you, what is the Black-Litterman model? Black-Litterman model is a reverse optimization process using the equilibrium price on the global asset classes. Okay, now of course, the equilibrium global asset classes, we assume that the weight on those classes are optimal. So we assume the market capitalization weights and market capitalization weight on those global asset classes, they are optimal. So we use that as a base and backward, or the reverse way to get the optimization for the asset classes. The purpose is to create a stable mean variance efficient portfolio, right? Which is cover the problem of the expected return sensitivity. Now we previously discussed that is a major problem for the corners portfolio or two-fund separation approach, is that the return estimation is so sensitive to the input parameter. So we are going to do here is using the Black-Litterman model to resolve this problem. In other words, we're not going to estimate the expected return based on historical data of the return, but we're going to use and on the other hand, we're going to use the capital weight and the standard deviation of the asset class and the correlation to estimate the expected return. That is very interesting. All right, so we don't use the sample estimate return, but we use the variance, standard deviation, and correlation matrix to finish that job. Right. So how do we do that one? I'm going to use the example here. Suppose the global market, right, we can classify by 5 different asset classes: U.S. bond, global bond, except U.S. equity, global equity except U.S., and emerging market. Okay, emerging market maybe we say here is the equity part. Now, we can calculate the capital weight based on the capital value of each classes. So we got this capital weights here, right? Like 15.62 and 21.97, 25.9, and so on. Then we got this one, our total 100%. So we got this weight. Now we assuming those weight are the optimal weight because these are the equilibrium condition, right? On the equilibrium condition. Then we estimate the standard deviation, all right, with respect to each class, each asset class. Then also we have the correlation matrix here. Right? This is would be the 5 by 5 matrix again, right? But with a different, it's a global classes, and you see again, and there's a negative correlation appear between that U.S. bond versus the U.S. equity and global equity and emerging market. So this correlation matrix play a very important role here. Then now the next, how do we use Black-Litterman model to calculate the expected return of each asset classes? Now our goal is to define the expected return because expected return is what is required return. Right? Then we can use that one to do many other things. For example, to calculate the optimal weight of the portfolio. Now, to achieve this goal, Black-Litterman say that we got to consider not just the we don't need to consider the estimate historical simple mean. We need to do is using the covariance matrix. So here one important part is covariance matrix. This covariance matrix on here, the center point. And then here is the capital weight. So here another piece of information important is the market capital weights vector. This is a 5 by 1 vector. Right? Matrix is a 5 by 5. So 5 by 5 times 5 by 1. So what is that? Okay, this covariance times the weight. That is the more like the we call a variance, total variance of the that in this market portfolio, the global market portfolio, all right, variance here. There's correlation times the weight. The weight, the combination of the variance covariance matrix here. Now, so it's a covariance. Remember, this is not just correlation; it's covariance. Okay. Now, the Black-Litterman say, okay, now not only that. Now, the purpose to do that one is I'm going to use that one times the risk aversion parameter with this covariance, with the market variance, then I can define this called the implied excess return. Okay, implied excess return. The implied excess return is the key. It's excess return meaning additional to the risk-free rate. So if I can get the implied excess return from the covariance matrix and the market weight plus risk aversion parameter, all I need to do is add that with a risk-free rate and I can get expected return for each asset classes because these are the matrix and vector. So basically there's a formulation here, the mathematical expression. Pi is the implied excess return, vector, right, is the 5 by 1, and then here's the risk parameter times the sigma is variance covariance matrix, and omega is the market weight vector. So here now I need to explain it to you about how do we calculate this risk aversion parameter. All right, so this parameter is equal to, all right, the global risk premium divided by the market portfolio variance. Okay, market portfolio variance. Now, so what does that mean here, right? So this is a premium. Premium means additional return for the global markets, global risk premium. For example, here, the global premium is a 4.14%. So that means that it's a global bond we estimate, not necessarily using historical data. But this is the estimate. The global risk premium is about additional to the 10-year global bond is about 4.14%. Okay, now this is the premium, but this premium actually will be dynamic, right? It is the premium dynamic. If and then it's related to what? It is related to the market portfolio risk. Then we calculate using a standard deviation. Again, this is a market portfolio, global. Then it's 8.09%. Now, this is standard deviation, so I have to take the square of that. So I get the variance. Variance is the parameter, right? We use for to calculate the um, risk parameter. Risk parameter. So risk parameter is if I got a premium 4.14%, but divided by the variance. So that means the premium per units of variance. So that is the premium per units of risk. So per risk units that the premium is there. So this is like every give you 1 unit of risk. What is a premium that investor want? 6.33. All right, this is would be a number. So this is an image number. So it's every risk in the global market, the investor requires 6.33 times higher than that as a premium they require to compensate that risk. So this we call the risk aversion parameter. So higher the risk aversion, meaning what? There's a higher premium required by, by every unit of the risk. So it's a risk parameter. So it's important because the risk aversion parameter change over time. You remember, we don't want to be just one static. So this could be changeable. That's the interesting approach. All right. So again, just remember that I implied excess return had a three parameter: the risk aversion parameter, covariance matrix, and the market cap weight vector. To do the calculation, the first one step to do is we need to calculate the covariance instead of just using the correlation. We have a correlation matrix. So the covariance matrix is the correlation standard deviation of the two asset class times their correlation, like y and z. So covariance between y and z is the standard deviation y times standard deviation z times the correlation yz. All right. So I give you example here. You can see by yourself. Now, I'm not going to show you the detailed calculation. It's just the format here. But the result I can show you from this table here, from this expression. This is the covariance matrix. Okay, this the covariance matrix is a 5 by 5, 5 by 5, and then we calculate this is the what? This is the risk parameter, risk aversion parameter, 6.33 per units of risk times the variance covariance matrix times this is the we call the optimal weight already existing in the market. By using this calculation, you see, look, pay attention here. We got this vector here. So what is this vector? This vector from 0, 1.22, da da da. These are the implied expected return for each asset class. Okay, that is the one we calculate. It's a 5 by 1 vector. The first element is the IER for bond, US bond, of course, 0, right? Because bond in here is risk-free, so there's no excess return. So plus the 4.63 is risk-free, of course. US bond is risk-free bond, 4.63%. And then you can see the next one is in addition, exclude U.S. bond. That is risky. So they imply riskier premium, right? The return we want is 1.2 additional. So that's the reason that the required return is 5.85. Then we can do the same thing for all of the asset. All right, we can get the all the expected return, and this expected return is the final outcome we want. For example, we can use that one to calculate this is called the required rate of return. We can calculate the value of each asset class if we know the cash flow. Or we can use that with the variance covariance matrix to define the efficient frontier, similar to like remember we have that one in the capital allocation line in the mean variance efficient frontier approach. All right, so these are the Black Litterman model.